Hi and welcome to another video in this discussion series. For this video, we will be discussing how the intermolecular forces of attraction that we have discussed in the previous video affects the different properties of liquids. And then afterwards, we will be discussing the solid state of matter. For the first one, how does intermolecular forces affect the melting and boiling point of a substance? When we say boiling point, the boiling point of a compound is the temperature at which a liquid is converted to the gas phase, while the melting point is the temperature at which the solid is converted to the liquid phase. So the strength of the intermolecular forces determines the boiling point and melting point of compounds. We take note that the stronger the intermolecular forces, the higher the boiling point and the melting point. So in boiling, energy must be supplied to overcome the attractive forces of the liquid state and separate the molecules to the gas phase. Similarly, in melting, energy must be supplied to overcome the highly ordered solid state and convert it to the less ordered liquid phase. A stronger force of attraction between molecules means that more energy must be supplied to overcome those intermolecular forces, therefore increasing the boiling point and melting point. So in comparing compounds of similar size, we can use this illustration here. So you have here the compounds with London dispersion forces only, which will only require less energy compared to those compounds with dipole-dipole interaction, and of course, compounds that can hydrogen bond. So an example here, which is methane or CH4 and water, they have similar molar masses, so you might expect them to have similar melting points and boiling point. However, methane is a nonpolar molecule that exhibits only London dispersion forces, whereas water is a polar molecule that can form intermolecular hydrogen bonds. As a result, the melting point and boiling point of water are much higher than those of methane, and in fact, the hydrogen bonds in water are so strong that it is a liquid at room temperature, whereas methane is a gas at room temperature. So in comparing two compounds with similar types of intermolecular forces, the higher molecular weight compound generally has more surface area and therefore a larger force of attraction, so giving it a higher boiling point and melting point. Thus, in our example here for propane, so this is propane and butane, they have both nonpolar bonds and they only exhibit London forces, but butane is larger and therefore has the higher boiling point and melting point. Remember from our previous video that the larger the molecule, the stronger the intermolecular force of attraction. So let's work on some examples here. For each pair of substances, identify the key bonding or intermolecular force and predict which one of the pair has the higher boiling point. So we have for our plan here is to examine the formulas and structures for key differences between the members of each pair. So are ions present there? Are molecules polar or non-polar? Is there a presence of nitrogen, oxygen, or fluorine atoms bonded to hydrogen? Or do molecular compounds have different masses or shapes? So before we work on our first example, we have to remember that bonding forces are stronger than non-bonding or intermolecular forces. And then hydrogen bonding is a strong type of dipole-dipole force. And lastly, dispersion forces are decisive when the difference is molar mass or molecular shape. Now for our first example, which is magnesium chloride, we have to remember that magnesium chloride is composed of magnesium and chloride ions held together by ionic bonding. Whereas in phosphorus trichloride, it is composed of polar molecules, so the intermolecular dipole-dipole forces are present. The ionic bonding forces in magnesium chlorides are stronger than the dipole-dipole forces in phosphorus trichloride, therefore making magnesium chloride with a higher boiling point than phosphorus trichloride. And then for our next example, CH3, NH2, and CH3F are both polar molecules of about the same molar mass. Now, if we look at CH3, NH2, it has a covalent nitrogen-hydrogen bonds, so it can form hydrogen bonds between its molecule. Whereas in CH3F, it contains a carbon-fluorine bond but no hydrogen-fluorine bond. So dipole-dipole forces occur but not hydrogen bonds. Therefore, CH3NH2 has a higher boiling point than CH3F. Because the hydrogen here in CH3F are bonded to the carbon atom but not to the fluorine atom. And then next, we have the following compounds. So in here, they are both polar molecules and both contain a covalent oxygen bond which can therefore form hydrogen bond. But in this case, this compound CH3CH2OH has a larger molar mass than CH3OH and its dispersion forces are therefore stronger. If that's the case, CH3CH2OH or ethanol has a higher boiling point than methanol. And then lastly, hexane and 2,2-dimethylbutane are both nonpolar molecules and therefore experience dispersion forces only as their only intermolecular force. So they have an equal molar mass but they have different molecular shape. So cylindrical hexane molecules make more intermolecular contact than the more compact 2,2-dimethylbutane molecules. Therefore, hexane has a higher boiling point than 2,2-dimethylbutane. The next characteristic of the liquid state would be the vapor pressure. So when we say evaporation is the conversion of liquids into the gas phase. So evaporation is endothermic. When we say endothermic, it absorbs heat from the surroundings. This explains why the skin is cooled as we sweat or as our sweat evaporates. And then when we say condensation is the conversion of gases into the liquid phase. Unlike evaporation, condensation is an exothermic process. When we say exothermic process, it gives off heat to the surroundings, and at equilibrium, the rate of evaporation and the rate of condensation are equal. So the vapor pressure, when we say vapor pressure, it is exerted or the pressure exerted by gas molecules in equilibrium with the liquid phase. So the vapor pressure exerted by a particular liquid depends on the identity of the liquid and the temperature. So as the temperature is increased, the kinetic energy of the molecules increases and more molecules escape into the gas phase. Therefore, vapor pressure increases with increasing temperature. So we also have to remember that the boiling point of a liquid is the temperature at which its vapor pressure is equal to 760 millimeters of mercury. Therefore, in terms of intermolecular forces, the stronger the intermolecular forces, the lower the vapor pressure at a given temperature. So, compounds with strong intermolecular forces have high boiling points and low vapor pressures at a given temperature. So, in this example or in this illustration, previously we learned that the water has a higher boiling point than methane because water can hydrogen bond with methane while methane cannot. So at any given temperature, water has a lower vapor pressure because its molecules are held more tightly and remain in the liquid phase. Now, for the viscosity and surface tension, when we say viscosity, it is a measure of a liquid's resistance to flow freely. A viscous liquid is one that feels thicker, and compounds with stronger intermolecular forces tend to be more viscous than compounds with weaker forces. Thus, water is more viscous than gasoline, which is composed of nonpolar molecules with weak intermolecular forces. So the size of molecules also play a role. The molecules do not slide past each other as freely, so substances composed of large molecules tend to be more viscous. Olive oil, for example, is more viscous than water because olive oil is composed of compounds with three long floppy chains that contain more than 50 atoms in each chain. Now, when we talk about surface tension is a measure of the resistance of a liquid to spread out. So, molecules in the interior of a liquid are surrounded by intermolecular forces on all sides, making them more stable than surface molecules that only experience intermolecular forces from neighbors on the side and below. So, this makes surface molecules less stable. And we have to remember that the stronger the intermolecular forces, the stronger surface molecules are pulled down toward the interior of a liquid. Therefore, the higher the surface tension. So because water has a strong intermolecular hydrogen bonding, its surface tension is high. This explains why water striders can walk across the surface and why a paper clip can float on water. Now, when a liquid is cooled so that the intermolecular forces are stronger than the kinetic energy of the particles, a solid state is formed. So solids can either be crystalline or amorphous. When we say crystalline, a crystalline solid has a regular arrangement of particles or it has a well-defined shape due to the orderly arrangement of the particles. And when we say amorphous solids, they lack orderly arrangement and have poorly defined shape. So when we say crystal, a solid is a crystal and it is composed of particles packed in an orderly three-dimensional array called the crystal lattice. So here are the examples of the crystalline solids. So there are different types of crystalline solids, and the five most important types of solids are defined by the type of particles in the crystal. So we have here the atomic solids, which is composed of individual atoms held together only by dispersion forces. We have the molecular solids, which is composed of individual molecules held together by various combination of intermolecular forces. The ionic solids, which is composed of a regular array of cations and anions. The metallic solids, which exhibits an organized crystal structure. And lastly, the network covalent solids, which is composed of atoms covalently bonded together in a three-dimensional network. So here are the examples of the different types of crystalline solids. We have the ionic solid, which is composed of oppositely charged ions. Example here is sodium chloride. And then we have a molecular solid, which is composed of individual molecules arranged regularly like water molecules. And then we have here a network solid, which is composed of a vast number of atoms covalently bonded together like silicon dioxide. And then we have the metallic solid, which is a lattice of metal cations surrounded by a cloud of electrons that move freely like copper. Now, when we say amorphous solids have no regular arrangement of their particles. They can be formed when liquids cool too quickly for a regular crystal to form. So very large covalent molecules tend to form amorphous solids because they can become folded and intertwined. So examples of amorphous solids would be rubber, glass, and plastic. So a glass is an optically transparent fusion product of inorganic materials that has cooled to a rigid state without crystallizing. And that's what we call as amorphous solids. So here is an example, or here is an illustration which compares the properties of diamond and graphite. And that's it for our second video in the discussion series. Thank you for listening.